To listen me speaking a little bit about debugging memory corruption in C++. My name is Mateusz Nowak. Let me introduce myself a little. I'm a software engineer and team leader from a few days. Actually at Habana. We have our office located in Gdańsk near airport. You may heard of the company if you were following meeting C++ broker. There was a job offer in jobs section there. What we do, in Gdańsk, we are enabling TensorFlow to work with Habana hardware, so our cards that are designed for inference and training of neural networks. Okay, quick talk for people who like have it visual. And let me firstly ask, who of you is first time in Berlin this year? This year, yes. And who is first time meeting C++ this year? More people. Cool. So let's get further. Who has more than a year of experience with C++? More than 5 years? More than 10 years? Who is in the standard committee? Oh. Cool. So let us go from the problem, and then we will see what are the possible solutions. So what are the data corruptions? Data corruptions are usually unintended changes in data, in the memory. Those could be when reading, for the times when read has side effects, because it can happen, and for the writing, when we obviously overwrite something important. Sometimes this is due to hardware failure. Some people face this if they are doing some bare-bones firmware or some low-level stuff. Usually caused by programming mistake, not knowing something or writing something wrong. And there are few well-known types of such mistakes. First of one is buffer overflow, which can happen when we read or write over the boundary of the memory buffer. So we have some buffer of n and we try to access something later. It can happen on stack or on a heap. Stack version has its separate name, which we will talk about in a minute. Next group of issues is use after free, which is for memory allocated on heap, when we obviously free the buffer and try to access it later. It can happen if the buffer is not freed, but the object that resides in this buffer was already deleted. Because in some cases we separate deletion of the object from freeing the memory, and can happen if we move from the object. So since C++11. Okay, so moving from gives us object in invalid state quite similar if we deleted the object but not free the memory. For the third group that I mentioned earlier, we have to know a little bit about the stack. So this is example of the stack for x86 architecture. First thing to know is that the stack grows backwards. So when we are adding new stack frames, so calling next function, we grow backward. So addresses go down. There are some important things in the structure. Most important being old stack base pointer value. So the address to which stack will roll back or roll up when we go out of the scope of the function, and the return address of the function being very important. In this example, we can see that we have some function which defines a single element array on the stack, and we try to write something to places behind the end of the buffer. And what happened here? we are actually writing to the field that has a return address of the function. So instead of jumping to a proper location, we can jump somewhere else. And some attacker may place some malicious code here, and we have a security breach. Okay. So once we know some of the most popular cases for data corruptions, we can go through some dark corners of C++ languages, so the traps, the languages prepared for us to fall, which may result in memory corruption. There are some. First thing that we have to notice, this is actual post from C++ Reddit. Someone complaining how hard it is to learn C++. You know. Yeah. You can look it up. There's a large discussion under this. And there are some points which are linked to this. First of all, pointers. Pointers which some of my friends point us the reason they will never ever again touch C++. Pointer can point to nothing. Pointer can point to anything that is valid, to invalid objects, so the one that was deleted, or to the memory in other memory space, like we have some device which has own memory space and we allocate some memory on this device, keep this pointer on CPU, and by mistake try to access this address. So instead of writing on the device, because the address spaces are separate, we can corrupt something in CPU memory. Okay. The other problem is the reference, which works kind of like the pointer under the hood. Can points to valid object, invalid object, move from object, and you can fall into the trap, because the difference, if you assign to the reference, you are assigning to the very value it refers to, not the pointer, let's say. So it can generate some issues if you are not careful enough. Okay, next trap that you can fall into is from the family of implementation defined behavior. Do anyone knows what SSO is? Yes, short sync optimization, and similarly something for vectors if the buffer is small. But for this case, it's actual issue I hit in production code. When you try to, when you have some, let's say, C API that needs to get some pointer to char, then store these pointers. You as a user of the API are still owner of this char array, so you have to keep it somewhere, store it somewhere, and you try to do something like this. You get some two strings, concatenate it, put it into some structure with handle which is returned from the C API, and the very string moving to this structure, thinking that, okay, string is here, but the buffer should be somewhere else, because it's just pointing to the buffer in memory. And return this context. Context looks like this. It's not copyable and only movable. Okay. And we have some program that is using it like this. Remember, the C API under the hood needs to have this string be alive through both calls to the API, the same string. And in this point we hit an error which is hidden, because compiler is able to do some optimization in this place. So if the buffer is small, it does not allocate it separately, but keep it as part of the string structure. So effectively, when we do move, we are actually copying the string to somewhere else, and the pointer we pass to our C API is lost, is invalid in this place. As I said, it can happen similar to the vector and possibly any memory buffer that has some implementation defined things in its specification. Okay, the other thing with strings is null termination. We have different, actually two ways of terminating the string. One, we have a null character at the end as a string terminator, and in the other case we can have string without the null terminator. As far as I remember, for example, USB standard uses the second version for transferring buffers. But most of the functions rely in C and C++ rely on this termination null character to work correctly. And we have three cases actually. We have case of C-style strings, which can or cannot have null terminating character. We have std_string when we do C underscore str or we do .data, we get always the string that is null terminated. And since C++17 we have also string view, which has very similar API to string, but can or cannot be null terminated depending on what we are viewing under the hood. So the trap here is to be aware what we are doing if we trying to just simply replace string with string view because there should be some performance gain. As in some places, it may result in us getting into memory corruption because something else is relying on this null terminating character at the end. So, next trap. A very large table. I guess it's usually not shown when learning C++. It is one of the things you learn when you hit the issue and try to debug something. How the constructors and assignment operators are generated by the compiler if we define the structure of the class. There is a set of rules when is something defaulted, what deleted, etc., etc. And you actually have to take care of this if you are managing some memory or some other resources. Because if we, let's say, allocate some memory buffer, or maybe go back to this string example, we have some array of characters and we forgot to delete copy assignment and copy constructor, and it was implicitly generated. So at some place we have bug, some memory corruption, and debugging. It happened that the buffer was actually copied instead of being moved, or we didn't prevent it from being copied when we wanted to have single resource, single access to the resource, and single owner of the resource. For this are the rule of 0, rule of 3, rule of 5, and that was rule of desdemowa to remember about. But you again learn it once you hit the issue, usually at least. Next issue is with new and delete. So there are a lot of them, and you can override them in different places. You have some default versions implemented by the library. You can override them on program level, so everything in the program uses your definition instead of the one which is default. And you can also override them in every class. So the version is selected. What is the problem here? That there are, let's see, 22 new operators up to C++20. There were none added, at least at the moment when I dumped this from the CPP reference. And we have 30 versions of operator delete. And guess what happens if we forgot about overriding one of them? Any guesses? No, not necessary. Any other guesses? Okay, so what happens actually is that the default version is called. So if we forget something on class level, then firstly it looks for the override on program level, and then it uses the default version. So let's say we have some class, we upgraded to newer standard, forgot deleting one of the operators that is added, and user decides to use this operator, and boom, the behavior is not what we expected. So that can lead eventually to the memory corruption. For example, because we use some memory pool that requires going through specific version of the new or delete, but it goes to the default, and the memory is deallocated, it starts being returned to the pool, and it can cause problems. Okay. That were some of the dark corners. I guess you could list more and more and more of the undefined behaviors, all the things that are implementation specific in this case. But that were the ones I thought of. The other thing is that what hardware can give you, what traps, what you have to know about the hardware not to fall into any traps. Okay, so on most modern architecture, memory accesses are done with some alignments, with some blocks, usually the power of 2, at least for bytes. There are some cases that are exceptions from this, but let's skip it for now. And the size of the access depends on the architecture. So we have 32-bit or 64-bit architecture. It can behave differently. We can have some specific microcontroller processor for some usages. It can behave different. We have some specific instruction set, let's say some vector instructions that can require different alignment, etc., etc., etc. Okay. The other thing you have to be aware of is cache, because for speed, most memory accesses goes through cache. We have two cases. First one in which we don't really care with coherent caches when flashing and validating cache is done kind of automatically, and the other case for incoherent caches when we have to manually make sure that data is in valid state in valid place. Again, each architecture has its own definitions, its own versions. If you are doing some bare-bone farmer, you must usually need to care about this or implement something on the operating system level. You can fall into a trap. One of them was described in the blog post by Rodrigo Kumper and Bernard Urban. You can Google this. It is a story about the ARM CPU in the Big Little version where they hit some issue with data corruption, and it eventually, after debugging and reading the CPU manual, happened that the big cores have different cache line sizes than little cores, and they have to be handled separately, differently. So it's again knowing the hardware and adjusting the code for the case. Okay, so once we know what are the data corruption, then we know how can we fall into them. Then we can look at some solutions how to prevent falling into them. There are some. Okay, firstly, we get to know what C++ gives us as a language for preventing the corruptions. We can do some defensive checks, bounce checking if not null, if size is not 0. The simplest thing, and everyone probably is doing this when allocating something or getting a pointer to the function. Then, with C11 compatible environments, so C++ 17, or Visual Studio in earlier versions, we have some secure functions to operate on the memory. Those one with _s suffix, but those are as secure as the programmer using is not lazy, because usually people are just using them as the versions without _s. So not using the option to pass source buffer size in addition to destination buffer size, but just using the same value for these two. So again, this is as safe as the programmer who uses it cares about it. Then we have some std memory manipulation algorithms. Copying the range, copying part of the range, or filling the range. Those should be preferred over those C-style operators because they are aware of the types that are in the containers and aware of the containers. Then we have smart pointers that should help us and are helping us taking care of the pointers in case of watching for the life cycle and making sure something is not out of the scope or not deleted at the wrong place. There are some traps like doing cycles with shared pointer, which will lead to not deleting the objects, but it's again a matter of being careful when using it. Also with the C++ containers, since C++11, we have add function which allows us to do range checking on the buffers. Operator with braces does not check bounds, so we can easily go out of the buffer which we are accessing to. Add should check bounds. However, if we are doing things which require us to set no exceptions, compilation flags, so effectively disabling exceptions, we may hit into the issue in environments in which we cannot easily do some recoveries, because throwing exceptions with no exceptions set will result in program being terminated. So if we cannot do recoveries easily, this is not an option. Okay. Then apart from what the language gives us as programmers, we have a set of tools we can use to prevent or debug the errors. Firstly, we have static analyzers. Some open source ones, some proprietary ones. Those are to be used during compilation time to look for some common patterns for errors in the code. For example, PVA Studio is doing a lot of noise recently. They putting a lot of posts like this, analyzing open source code for the errors that can be easily detected and fixed if the analysis is run. And they are proving the value of such products this way. Then after the static analyzers, at the compilation time, we can do some things with compiler, use the proper flags. First set, wall extra and W pedantic is, in my opinion, the basic set which should be always used to detect possible errors. In addition to it, we have some other flags. First two being different versions between Clang and GCC for detecting use of uninitialized variables. Then we have flag to detect non-virtual destructors. So the case when we have class polymorphism and we forgot to mark the base class destructor as virtual, which will lead to this destructor not being called, which may result in leak when we allocate, for example, some memory or open some resource, and we won't close it, etc., etc. So this is for this range of problems. We have WEFFC++, which can help in detecting uninitialized class members. It gives a lot of false positives in case we have carried bases in class initialization for members, but from time to time can be run to detect some issues and look from the manual way. And we have walls of different warnings that we can find in the compiler's documentation that actually, when we hit the issue, we may look for something which may be for our case. Then in Clang, there's a in development feature that is called consumed annotations. This is pretty useful for the case when we have some issue with moving objects, because we can mark the class properly to show which functions can be called only in unconsumed state, and then on moving mark the class object as consumed, and then generate a proper warning in the compile time. Let's see the example. Say we have some API to open, close resource, and then execute on the resource. Something in some C++ array class, which is move only to handle this resource. What can we do with this? We can mark it as consumable with default state unconsumed. Then on constructing, again, we mark the state as unconsumed. The execute function can be also only called when we are unconsumed states, so effectively the resource is owned by the instance of the class. And when we invalidate the object, so which is called during the move from or move assignment operator from, we mark it as consumed. So the resulting class look like this, little bit different. But when we do something like this, so we create resource, move it to someone else, and try to execute something on it, if we set proper compilation flag, we get an compile time error. We are in wrong state when trying to do something with this class instance. As I said, it's in development. I haven't found the way to generate some warning in this case, so double move from. Maybe someone has some idea that can post or talk about later. Okay. So, sanitizers. Yeah. There are a bunch of them. There are runtime features as opposed to those compile time that I was talking about a few minutes earlier. We have different groups of them. They are available both in Clang and GCC. Ones for buffer overflows, data races, some undefined behavior, and stack protector, which was there previously. Very useful tools, can work quite fast. Can be enabled with compilation flag, so we have to recompile to use them. Important things, no optimizations, and enabling all symbols to prevent false positives resulting from the optimizations, and to have all the symbols to generate to have the nice call stack in the end. As I said, simple flags to enable them during compilation. And now the example with the other option, at least for other sanitizers, we can run it without precompiling the binary. We just LD preload the ASAN library, and if doing something like, for example, this allocated memory that is not read during runtime, we get pretty nice error pointing out the place which is broken. Important thing with this to remember is, unless we configure it differently, it would terminate on the first error hit. So we do not necessarily gather all the problems, but break on the first one that is hit. And Asana is so cool feature that Microsoft decided to support it with its native toolchains or MSVC since some late preview version also has support for this. And what is more important than didn't forked the sanitizer repository and did their own version, they are contributing to the version that is used by Clang and GCC. So all the compilers are using single tool for this, which improves it and allows us to use the same thing in different places, similar way. Okay, so apart from sanitizers, which are quite fast, we have some more heavy-duty runtime analyzers like Valgrind, Electric Fence Duma, and I saw recently something called GWP Asan, which is from what I read similar to Electric Fence. And also we have some tools from Microsoft, both from user space and driver space. They are a lot heavier. They make us the program to run much longer. So I treat them as last resort because they do give a lot of false positives, and you have to scroll and look from the huge logs, which takes a lot of time to find the issue. It's much quicker to use the other tools at first. Okay. And now the question, after what I saw up until now, who likes C++ little bit less because of the traps? No one. Everyone still loves C++. Yeah, cool. Who likes C++ more because of those traps? Yeah, cool. Okay, so sometimes we have tools available, but in some environments, let's say we have some esoteric architecture that has only compiler but nothing else, we cannot use them because we would have to implement the support from them, from all the porting, etc. It's much easier to do something manually to detect the errors. First of all, we can tag the memory. So when allocating the buffer, we put some special value before the buffer and after it, giving the user the pointer, which we would give usually, so the one without the special values. And when freeing the buffer or deleting the object inside, we check if those values weren't overwritten, so someone didn't destroy what we have there. On ARM architecture, there are some built-in instructions that are for this, so you can trigger this with some compilation flags, if I remember correctly, and have this without any further needs for implementing this yourself. Oops. Okay. Then apart from tagging the memory, we can track all the allocations, record the allocation size and place, and when destroying, check if it was delocated, and in the end, look for the things that weren't destroyed. So this is one of the ways to checking if we don't have some leaks somewhere. Also, we can have memory pools, which kind of limit the space in which our program allocates and delocates. This can be made using different techniques. I like the PMR very much because it's kind of giving the whole memory pooling at zero cost. And I believe it will be a game changer once for the embedded space and for the people doing things like this. Once the tool chains that the people use for these cases start to support this. And it's still not happening, as far as I know, so quickly. Okay, then we can handcraft checking for stack smashing using nice C++ code, which is pretty generic, so can be used for freestanding functions, can be used for class member functions and static functions for the classes, which are actually kind of the same as freestanding functions. This example needs still some adjustments for cases like stud functions and lambdas, because I haven't crafted it for it, but it should be doable. Okay, so let's start from the usage example. Let's say we have some freestanding function, some structure with static function and member function, and then the example using it. You can notice the func caller here being replacement for direct function call. Ugly macro, but I haven't found better way for doing this. We are instantiating the object of stack smashing detector, giving it a void for freestanding functions or type of the class, and then instance of the class in the class member function case, and the pointer to the function. What we can do then with it, using template magic, we can enable one of the constructors for the detector and initialize the class either with object pointer, null pointer, in case if we are playing with freestanding functions, or static class functions, or pass the instance of the class and store it to the, here for help for making it easier. Then we have operator parentheses, which gets the function to be called and calls some helper structure, create some helper structure instance and return it. This function T is pretty nice. Here it can be automatically detected which type of function is called, so the one for the class member and the one for the freestanding. We have ellipses for the arguments, so we can pass any number of arguments, and all the types using these helpers can be detected, so we don't need to pass them explicitly. Okay, so then we have our helper structure, which is keeping the function pointer, reference to the detector to be able to access the object pointer if we are in an object member case. Instantiate it with the function pointer, as I showed it's done here. Okay, and again, operator parentheses, which is what is important, has to be not inlined and not optimized to prevent this canary value being reordered into some weird place, to have it always placed at the beginning of the stack frame. And some, again, helper macro not to repeat the code for checking the canary values and aborting if error happens. And again, nice feature if context for the case if we are returning void, or the other part will be for returning some value. We are just calling the function for the freestanding or class member case, and then do canary check after the function was called. And the other branch for the returning the value, we have to store the value somewhere before checking the canary and returning. A little bit template magic, pretty nice thing to be done. And as the last thing I would like to talk about is the importance of having a colleague and a person in your team that you can talk to, that can review your code, and then that can sit with you and talk about these things that you can learn from or teach. Because this way you can have a different view on the code. The person may see something that you have missed, or tell you about the issue that he or she recently discovered and resolved the similar issue, because it just makes it a little bit quicker to resolve the issues if you constantly learn. And this is one of the reasons why I came here to this conference, to talk to you, to share my experiences and show the things that I shown here. And that would be all for now. Here are my contact information. There's a GitHub link. The stack smashing detector that I showed is there, so you can check it out there and play a little bit with it. Probably implement the missing part for stud function or for lambdas. Also, the slides, apart from being published by the conference, will be there. I believe tomorrow you should be able to download them from there. If you don't want to write down the contact, I have some have also my personal business cards, so you can come and get one. And also, again, this is Habana sticker, pretty cute one. If you need to get to know about Habana, there are some company business cards on the table. You can pick up one to have some starting point for looking further. Any questions? Here's a question. Please wait for the microphone because we have to have one. Okay.
I would recommend you heap track as well as a runtime profiler. You can detect some memory leaks there, but yeah, it's really nice and it's not so heavyweight as Valgrind. So if an if Valgrind takes like 24 hours for running something very heavy, heap track will be maybe like 40 minutes. So
okay, so something in range of sanitizers, yes?
Yes, yes.
Okay.
But it's a runtime sanitizer, so you get memory leaks, memory leak impression, memory footprint, and it's really nice.
Thanks for this. I will take a note and update the slides so it will be there. Any more questions? Okay, here's the question.
So what is the advantage of using a custom-made stack protector compared to the built-in stack protector?
I wouldn't say there are much advantages. This is the last resort option when you don't have this in your toolchain.
So this is for the case when you don't have a compiler with a stack protector?
Yes. Yes, you can use it also when you have stack protector built in, but as usual, first use tools that are available, then go to the cases which are not covered by them. It will save some time.
Thank you.
More questions?
Okay. So, thank you.
Thank you very much.